Hi students, it's Dr. Marks, and our topic for today is the law of large numbers and the central limit theorem. Now, if you were a statistician, you'd be saying, woo, because this is pretty cool stuff. We're going to go through it carefully so you really can appreciate these two things. Let's get started. Now, in this lecture, as I said, we're going to introduce two important laws or theorems from statistics: law of large numbers and the central limit theorem. And these are both going to motivate why we need large samples. If I try to just boil it down to one thing, that's really one huge takeaway from these. We're going to look at theory just a little bit. Don't be scared. But then we're going to make connections to both research and to some different industries that rely on these. For us to get started, we have to go back to the idea of a random variable. And we've talked about random variables before. Remember, we use capital letters for our random variables, so let's use x. Let's let x be a random variable. And so when we say x is a random variable, we're saying that the possible values of x depend on the outcomes of a certain random phenomena. A lot of words there, right? The possible values of x depend on the outcomes of a certain random phenomena. But really, we're just saying that there's a set of values from a random experiment. So let's keep it simple. We have been working with random variables. For example, we could talk about the result of drawing a card out of a deck, right? That is a random event. So we have a random variable. Now, we can take some draws of x, whatever x is. So let's say we're going to take some draws for this random variable. So it would be like taking, a deck of cards and drawing one card and putting it back and taking another draw and putting it back. But let's say that we get x1, x2, x3. And so then we can compute a sample mean. And that sample mean is going to be noted as x bar. We use that bar, x bar, to tell us the mean of the sample. But here's the thing. We've just computed a mean of our sample, right, from drawing x, but it's not necessarily identical to the population mean. And when we talk about population means, remember, we use mu. So we've got two different things potentially, a sample mean and a population mean. Remember that our goal here in statistics is to learn about the population. But most of the times, it's impossible for us to survey the whole population, right? So how do we learn about the population? We do it from samples. So we've seen this kind of diagram, but kind of in the opposite before, because before we were talking about drawing samples from a population. Well, now we need to be thinking about, I'm going to use my sample to infer about my population. So that's why I have the arrow going from sample to population, because I'm going to use a sample to infer about my population. And if you think all the way back to Module 1, at the very beginning, we talked about the idea of inferential statistics, using our samples to make inferences about our population. So that's kind of where we're heading here in this module. So let's start with the law of large numbers. The sample mean, x bar, and the population mean, which is mu, well, they're related by the law of large numbers. The sample mean can be brought close to the population mean. So in other words, I can make them more similar by enlarging the sample. So think about what that means. Remember, we want to learn from our sample about our population. So by enlarging our sample, the sample mean can be brought closer to the population mean, which is what I'm trying to learn about in the first place by taking samples, right? So that's pretty cool. In other words, let's say it another way, if the sample is large enough, then we know mu equals x bar. So if the sample's large enough, then we know the population mean and the sample mean are going to be equal. Now, I realize you're probably having trouble appreciating how cool that is. But one more time, let's just remind ourselves that the whole reason we take samples to begin with is to learn about our population. So if I can simply make my sample bigger and bigger, and therefore get a sample mean that better reflects the population mean, well, that's cool because it's allowed me to learn a lot about my population statistic, right? My population parameter. So, in summary, the sample averages are going to converge to the population mean as sample sizes increase. Let's look at this graphically because I think that will help you out. Now, you've seen this before. We're looking at number of coin flips. So look along the horizontal axis and you see number of flips 10, 15, 20, 25, 30, right? We're just going from 10 all the way to 200, right? On the vertical axis, we have the proportion of times the coin lands on heads. Now remember, a fair coin should be 50-50, right? But that's not what it's going to look like when I take my sample. Let's focus on a small number of coin flips. When we have a small number of coin flips, we see, look, my first 10 flips, I've got only, 30% landing on heads, which means 70% is on tails. Well, that's not right? Shouldn't it be 50-50? Well, then I keep flipping my coins and it goes all the way up to 70-something%. Now I've got 73% landing on heads. But now, as we continue to flip, more and more and more flips, so we're up to 130 flips, 140 flips, 150 flips. We're going to see this proportion come to about 50%. So it converges to 50% because we know, right, a fair coin should be 50-50. But I flip it once, it's not going to necessarily be 50-50. If I flip it, right, it's going to land on heads. If I flip it 5 times, it might not land on heads only half the time. Same thing for 10. But what we're trying to say is if I keep flipping and flipping and flipping and flipping and flipping, eventually we're going to see this 50-50 split. If you don't believe me, take out a coin and do this experiment yourself. This is a pretty standard basic statistic experiment that you can run with students. And so people do that, and that's how we get this kind of graphic. So somebody clearly played this, and they determined that eventually, by 200 flips, it converged to that 50-50. All right, you get the idea. Now, who might care about the law of large numbers? Well, one industry that cares about the law of large numbers is casinos. Casinos have to rely on the law of large numbers because that's going to help them ensure profitability. So let's think about just one person, right? Everyone agree that an individual may get lucky and win here or there, right? So you get one friend, they go in and they make a good chunk of money in the casino, and that happens. So if we look at just a handful of outcomes where, I might get a few people that get lucky, well, it might look like a casino could lose money. But we know that doesn't happen, right, guys? We know that casinos never lose, right? Well, why? Because of the law of large numbers. So while one person might have some winnings, is everyone going to have that same type of success? Of course not. So over the course of thousands of individuals, right, because it's not just 2 people playing at a casino in a night or 5 or 8 or 12, it's going to be tons of people, right? They're going to be crowded casinos. Over the course of 1,000 individuals, if it's not tonight, by the end of the week, we've got thousands of individuals. Now the winning percentage becomes more predictable. And gang, when that winning percentage becomes more predictable, well, that's the law of large numbers at work. So we can look at the same kind of graph that we just looked at for coin flips, where we started with 1 coin flip and then 5 and then 10 coin flips all the way to 200 coin flips. but instead of coin flips, let's let it be gamblers. Well, on the horizontal axis, we've got number of players in a casino. And on the vertical axis, we have the casino. Also, somebody spelled it wrong. I took this from somebody else. A casino profit percentage. So how profitable are they going to be? Well, let's start by looking at when there's just a few players. I mean, look at it. When there's just one player, they might actually have losses, right? Do you see for the one player, we're down in the negative percentage? Well, a negative percentage would be a loss, right? So we go from loss, and now we add a second casino player, and all of a sudden, boom, we're in the clear, right? We're making like 60-something, 70%. And do you see the randomness there? Until we keep adding more and more and more players. And look what happens. It's going to converge to a more predictable percentage. So what we see here is this has converged to a positive percentage for the casino. And that's how casinos make money, right? That they're not making money when we just look at one or two people, but over a very large number of people, right, over a large sample, the proportion of wins is going to converge to something that they're more easily able to predict. The insurance industry also relies on the law of large numbers. So again, just like casinos, that's how they stay profitable. And when you think about the insurance industry, it's all about claims, right? How many claims? Well, clearly there's going to be some number of claims. If we're talking about, let's just take a year, for example. In a year, we know there's going to be some number of claims. And when there's claims, then the industry clearly knows they're going to lose money on some people this year because there'll be some proportion of people that make claims. But do they insure just one or two people? No, that would be highly risky. The insurance companies providing insurance to thousands of individuals. And of course, we know those thousands of individuals all pay a premium. And so when only a portion of them need to file a claim, then we know that with a very large number of clients, the whole situation with respect to profitability and risk, it becomes much more predictable. So with large numbers of clients, you can figure out a forecast. How much are we going to be paying out for accidents and house fires and those kinds of things, making it easier to forecast profits. So again, insurance, the whole profitability model is based on this idea of law of large numbers. Be clear. If they only had a few clients, this would not be something that they could predict. It would be really difficult if you just had kind of two big clients. It would be very random. An example that I didn't know about, I didn't think about until I started doing more reading and research about what would be some good examples here, is the renewable energy industry. Now, this is, I think, an interesting example. Clearly, with renewable energy, we have two important forms of renewable energy. Let's talk about wind and solar. And we agree that generating wind energy and solar energy requires both windy and sunny days, depending on what we're looking at. Now, weather is something that they don't control. So clearly, they're not going to be able to produce energy 100% of the time. There's going to be days with little wind. There's going to be days that are less sunny. And so you can't reliably know that you're going to produce energy every single day, all day long. So for this reason, companies establish many thousands of wind turbines and solar panels. In other words, they kind of diversify, and they're going to diversify across different locations because, of course, different locations have different weather patterns. And on a certain day, they're going to have different weather. And they're going to connect those tons of different wind turbines and solar panels to the same grid. When they do that, then they've got a good chance of sustainably producing energy. But we understand if there's only a few wind turbines or solar panels, then they're not necessarily going to be able to reliably generate sufficient energy. So again, law of large numbers comes in because with many of these different things in different areas, diversified in that way, even with unpredictable weather patterns, because you never know when you're going to get lots of sun, right? You've got a forecast, but you don't know 2 months from now. The bottom line is it's easier to forecast energy production in this way. So again, law of large numbers at work. So how does this apply to us as analysts, as researchers, or people that might want to be involved in research? Well, one thing we have to think about is the idea of sampling. So let's think about our samples, A and B. And when we think about sampling, we need to be thinking about the law of large numbers when we decide how to design our research when it comes to data collection. We know that if our samples are small, then they might not look very similar. So imagine taking very small samples of students or very small samples of employees. There's no guarantee that sample A is going to look anything like sample B. I might kind of by chance end up with, all women in sample A and all men in sample B, or upper level management in sample A and lower level management in sample B, right? If I'm really taking samples, what do I need to think about? They need to be larger, because as our samples get larger, they're going to look more alike, right? As our samples get larger, they better reflect that population, right? So when we're thinking about doing our own research, we need to be careful when using small samples. You can really have misleading results from small samples. That means when we're looking at the research of others, maybe you're reading about studies, especially stuff we see in the news or on social media, since of course we know that's a good source of reliable statistical work, right? But when you're looking at stuff and you're reading stuff, you need to ask a key question, and you should always be thinking about, hey, what is sample size? Because I know, gang, all of us have seen studies with really small sample sizes. And the bells should be going off for you, because you need to ask yourself, what does that tell you about the ability to learn about the population when your sample is really small? And clearly, we don't want to have inaccuracies, right? Do you perform medical trials when we're looking at new pharmaceuticals on just small samples? Of course not. My brother used to own a pharmaceutical research company. And when a new drug is being proposed and is going through FDA approval processes, it has to go out for testing. And he would do testing, but he would be just one of many different sites doing the testing. So clearly, large samples is going to be more reliable. Our sample means are going to better reflect the population means when we have large samples. Let's move on to the second topic in this lecture, and that is the central limit theorem. The central limit theorem is the basis for a lot of statistics. And for this reason, it's very, very powerful. And if you're a statistician, you would say, oh my gosh, the central limit theorem is really cool and it gets me a lot of mileage. It really makes it easier for me to do certain things. The central limit theorem basically says that as we take an increasingly large number of samples, so as we take more and more samples, right, from our population, the distribution of sample means approaches the normal distribution. The distribution of sample means approaches the normal distribution. Now, gang, it is okay if right now it sounds like I am speaking Greek, because I'm going to illustrate this to you. But let's look at the first part. As we take an increasingly large number of samples, we're just saying, hey, as we take more and more and more samples from a population, the distribution, so we're going to take a distribution of sample means. We understand that part. So I'm going to take a sample, calculate a sample mean. I'm going to get a whole bunch of them. I'm going to find a distribution. That distribution approaches a normal distribution, the normal distribution, which we'll talk about. So basically, this is a statement about the shape of the distribution. I know it's a little confusing. Bear with me. I will get you there. Now, why is this cool? Well, we understand the normal distribution. And you're going to see in a few minutes that the normal distribution has specific characteristics. And so it's giving us something to work with that we understand and we know the characteristics. But on top of that, many statistical techniques assume a normal distribution. In other words, you can really only use them if you have a normal distribution. So the central limit theorem has just told us, hey, under certain circumstances, you have a normal distribution, which means, yay, we can use these statistical techniques. And we can use them because of the central limit theorem. All right, stick with me, guys. I know this is very abstract. So let's start with our population there on the bottom right. And we take a bunch of samples. So I've got sample A, sample B, sample C, sample D. We're pulling samples from our population. You understand what that means, of course. Now let's let these samples that I just showed you, sample A, B, C, D, and I'm going to have more. So A, B, C, D, E, whatever, be sufficiently large. We'll talk about sufficiently large, but they have to be sufficiently large. In other words, they need to be big enough, whatever that means, but we're going to talk about it. Now, we're going to compute a sample mean for each one of those, right? So we take sample A, find the mean. Take sample B, find the mean. Take sample C, find the mean. You get the idea. So now I have a bunch of samples and I've calculated the mean for each one. Then I'm going to create a frequency distribution of those means. In other words, I'm going to plot the distribution of the means so I can see what it looks like. And when I take that frequency distribution of these means, it's going to approach the normal distribution, right? So as long as I have sufficiently large amounts of samples, it's going to approach the normal distribution. And again, why do we care about that? Because the normal distribution's cool. It's useful. It has characteristics we like. It is the underlying assumption for a lot of statistical testing. And that means we can use these tests. So again, this is a statement about the shape of the distribution. And one thing that's really cool is that it doesn't matter what the shape of the population distribution is, right? The population from which we pulled the sample. It doesn't matter what the shape of that distribution is. When we pull our samples and take our means and create a distribution of our sample means, we are going to get a normal distribution. So this gives us a lot of flexibility in that we can use these statistics that assume a normal distribution because we have one. All right, I know, still a little abstract. Stick with me. I'm going to make it more concrete. Now, you're going to see in a minute that a normal distribution is bell-shaped. So what we're saying is that when we take these sample means, we create a distribution, the shape of the distribution of the sample means is going to begin to look bell-shaped as well. And that's going to happen as our sample size increases. We take more and more samples. So again, how does this help us out? Because normal distributions have particular characteristics, and that allows us to use that information. So let's use the example of rolling a die, and we're going to roll it first just once, then twice, then 3 times, then 4 times, 5 times, on and on and on and on. And then what we're going to do is create a histogram. And what you're going to see is that this histogram is going to start to look different as my number of samples gets larger. So let's do that. All right, we roll our first die, and I'm a little unclear why they don't have these as equal probability, but they don't. But probably they should be equal probability. So do you agree? I roll a die and I have a probability of a 1, 2, 3, 4, 5, 6 with equal probability. It doesn't matter so much that that's not an equal probability as represented. Now, Instead of rolling just one die, let's roll 2. So now we have 2. All of a sudden, remember, my numbers, instead of ranging from 1 to 6, now range from 2 to 12. And do you see that I have multiple ways to get 5, 6, 7, 8, right? There's only one way to get 2, right? Let's look at the ends of this distribution. There's only one way to get 2, right? Snake eyes. There's only one way to get 12, double sixes. But there are different ways to get 7, for example, right? I could have 3 and 4, 5 and 2, 2 and 5, 4 and 3, 6 and 1, right? 1 and 6, you get the idea. So we're starting to see all of a sudden a little more of a bell shape, but it's still not there. Let's roll 3. Now we see with 3, we're seeing a distribution go from 3 to 18. Starting to look a little bit more bell-shaped, am I right? So let's keep rolling, adding a die each time. Let's look at 4, and now 5, and now in the bottom right corner, 6. Do you see what's happened here? It's starting to get really bell-shaped looking, where a lot of that frequency is sitting in the middle, right? With that center of that bell-shaped distribution. Now, here's another depiction of the same thing, and I like the other one better because it shows you the dice, but this one for one die has that equal probability. If you look at the very top left, had to figure out which one was my left hand for a second, top left with the blue, you see when I have just one die, we have an equal probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6. So I think that's really how the other one should look, but I liked that graphic better. So again, this is just the same thing being represented in a different way. But I want you to look at this because I want you to look at the bottom right picture. That's what's missing in the previous diagram. So neither one of them is perfect. But do you see in that bottom right distribution, when we go from, you can see kind of it's very soft, I know, but look at the green, it's kind of wider. And then you see yellow, it's getting a little bit more narrower, less weight in the tails. And then it gets red, even more narrower. And then as we continue to roll an extra die, we're going to get closer and closer and closer and closer to that normal distribution. And you see that there. The weight in the tails starts to shrink as n increases. So make sure you're seeing this, that less weight in the tails, right? So when you compare all across those different colors, the tails have less weight. The tails are getting skinnier and skinnier, I guess could be a way of thinking of it. Now, we talked about just a second ago if samples are sufficiently large. So what do we mean by that? What is sufficiently large? And the standard textbook discussion is generally suggesting sample sizes of 30 or more. If we have samples of 30 or more, then it's suggested that the central limit theorem holds. But keep in mind, there's other reasons to have larger samples, right? And we've talked a little bit about this already. So how does the central limit theorem help us? Well, as we've said, because normal distributions have particular characteristics, and if we know we have a normal distribution because of the central limit theorem, then we can use that information. And as we've already said, because statistics that we might want to use assume a normal distribution. Well, I have a normal distribution under these circumstances, so yay, now I can use these statistics. For example, if we want to run significance tests, well, that assumes a normal distribution. And so when I check that box, in other words, I can now validly run significance tests. But let's talk about the normal distribution before we go any further. I know you're probably familiar with the normal distribution, and so we've been using that term bell-shaped, right? You're looking at this, you're saying, yeah, this is bell-shaped. So we have a bell-shaped distribution we know that it's going to have a mean right there with my red line in the middle going through the peak. And then we also see that the cases here are symmetrically distributed about the mean. In other words, right, if I folded it in half, the left side and the right side would be identical. So that's what we mean by saying that the cases or observations are distributed symmetrically about the mean, right? It is the same on the left as it is on the right. We can also talk about the spread. So if you look at my arrow that I just imposed there, we've got this idea of spread. How spread out is this distribution? So the extent of the spread, right, this idea of dispersion, the extent of the spread of the data around the mean is measured by that idea of standard deviation. So we've talked about standard deviation, right? It was one of our measures of dispersion. Now, to refresh your memory, we could have small standard deviation like we do on the left. If we have a small standard deviation, then we know our spread is not very big. So you see that distribution on the left that's really narrow and tight. And on the right, we see a large standard deviation. So we see a much greater spread. So remember, standard deviation is a measure of spread. Now, there's some areas that we're able to measure. Look at those tails where you see the shaded in area in gray on the left and the right at the very end of the tails. Well, we can measure what falls beyond 2 standard deviations above the mean. So what you're looking at right now in those gray areas in the tail is the areas in the distribution beyond 2 standard deviations above the mean. So in a normal distribution, it turns out that 95% of the values will lie within 2 standard deviations of the mean. So look at my arrows there to the left and to the right. I've measured 2 standard deviations to the left and 2 standard deviations to the right. So what we're saying is it turns out if you look at that part of the distribution, 95% of the observations will lie within 2 standard deviations. So 95% of observations are going to fall in that area as opposed to falling in the tails. So remember I said just a minute ago that normal distributions are cool because they have certain characteristics that we understand, that we know, and we can use. Well, here you go. Here's an example of what I mean by that. Well, I can use this idea that 95% of the values will fall within 2 standard deviations because that's a standard characteristic of the normal distribution. So let's say we have a normal distribution and it has a mean of 100. So you see I've put that mean there on the horizontal axis at 100. If we randomly sampled a value from this distribution, so I've got this distribution with the mean of 100, and if I randomly sample from this distribution, I'm going to randomly draw, in other words, there's a 95% probability that the value that I just drew would be within 2 standard deviations of 100. So guys, I know that's really abstract and you're thinking, okay, Dr. Marks, why do I care about this? Well, you will. But think about what that tells us. It gives us some idea about our degree of certainty, right? There's a 95% probability that the value that we draw from this distribution will be within 2 standard deviations of 100. So that tells me I can be 95% confident that when I draw from this distribution that there's a likelihood that my observation is going to be within 2 standard deviations of this mean. I can say that with 95% confidence. We're going to be coming back to that idea. I don't expect it to mean a whole lot right now. It's still a very abstract concept, but please hold on to the idea that the normal distribution has some characteristics that mean we can kind of talk about certainty, like what I just said. I can be 95% certain that when I draw an observation from this distribution, it's going to be within 2 standard deviations of my mean of 100. Now, there are other characteristics of the normal distribution. They work pretty much like what I just gave you for 95%. It turns out that 68% of the data falls within 1 standard deviation, right? That's narrower, right? A narrower width, because 1 standard deviation is closer to the mean, right? So 68% of the data falls within 1 standard deviation of the mean. We've already said 95% of data falls within 2 standard deviations of the mean, and 99.7% of data falls within 3 standard deviations of the mean. So make sure you understand. 1 standard deviation would be more narrow. 2 standard deviations would be wider. 3 standard deviations would be even more wide. So it makes sense within 3 standard deviations of the mean, since that's a wider area, we're going to have more of the data falling in between plus or minus 3 standard deviations of the mean. Please take a quick look at that diagram and just make sure it makes sense to you. So again, we're talking about these characteristics of the normal distribution that are going to become useful for us when we want to talk about certainty. How certain are we that an observation will fall in this range? Now, why do we care about the normal distribution? Well, assuming our data is normally distributed means we know the properties of the distribution, right? We just looked at some properties of the distribution. And that means we can use these properties to assess the likelihood of some outcome, right? We just said I can be 95% certain that if I draw an observation from this distribution that it will fall within 2 standard deviations of the mean. That's helpful information. And so that's going to give us a way of determining if one hypothesis is more plausible than another hypothesis, because we have now these kind of degrees of certainty. I'm only 68% certain that it falls in this range, but I'm 95% confident that it would fall in this other range. You get the idea. We can use what's called a t-distribution. And the t-distribution is going to be really helpful when our sample sizes are smaller. So the t-distribution is going to allow us maybe just a little bit more mileage, if you'll let me explain it that way. So what's next then? Where are we going from here? Well, in the next lesson, we need to explore the idea of a t-distribution. We need to explore this t-distribution because we're going to be using this t-distribution for the rest of the course. For those that remember some of your statistics, you remember using that t-table, right? Over and over and over again. We need to understand it. We need to understand the t-distribution, and I'm going to be teaching you how to use a table that summarizes its characteristics because we need them in order to do hypothesis testing. Now, we'll also kind of do some shortcuts as well when we get to regression for those of you that have had some of that and you understand the idea of p-values. But we're going to start by looking at the t-distribution, understanding how to read a t-table, and then we'll employ it in hypothesis testing. Let me know if you have any questions, gang, and thank you so much for listening. Have a fantastic day.